So taking a look at this question, which statement about the reactions of halogen alkanes with aqueous sodium hydroxide is correct? So what I want you to do is pause it right now, the video, and give it a try, and then unpause it, and we'll take it up together. Okay, so if you chose A, primary halogen alkanes react mainly by SN1 mechanism, then you're wrong. But why are you wrong? So if you remember, there was SN1 and there was SN2 mechanisms. The SN1 mechanism was for tertiary halogen alkanes. And the SN2 mechanism was for the primary halogen alkanes. And so here, this is saying the primary is SN1, which is incorrect. The primary halogen alkanes undergoes an SN2 reaction. But let's take a look at the mechanism. I think it would be useful to answer this question. So let's just take a look at that for a second. This here is the SN2 mechanism, and this is for a primary halogen alkane. We see this is primary halogen alkane because you notice the bromine is attached to a carbon which has only one R group. So this carbon has only one R group attached to it, and so it's primary. Now if we look at this mechanism here occurs in one step only. This, what you're looking at in the middle here, is a transition state. It's not an extra step. It's the transition state. So what's happening here, if we take a look at it, what's happening here is you have the carbon and the bromine is breaking off and the hydroxyl is attaching. And this is our transition state, and these electrons are going to be going towards the bromine, and the electrons from the OH minus are going to be forming the bond. And so what you have as a result, that the bromine will come off, and you will see that there, and then the OH attached to it. And notice that there's also an inversion of the stereochemistry, meaning where the Br was on this side, the OH is on the opposite side. And so this happens with a primary halogen alkane, and this is a one-step mechanism. Now here, what we have here is a tertiary halogen alkane, and what we got there is going to be a two-step mechanism. So here are our two steps, right here. Step 1 and step 2. Now, one thing you notice, so the tertiary halogen alkane undergoes a two-step mechanism. Now, one thing you notice in this two-step mechanism, how does that happen? First, see, this bromine will come off. This then forms a positive carbocation. You notice the charge right here because the bromine took the electrons. This bromine took the electrons. It's negative. You got the negative sign right on the bromine there. It took the electrons, and so the carbocation is become positive. This is known as the slow step. So the first step is the slow step. Then the second step is where the hydroxide attaches to the carbocation, making your final product, which is an alcohol. So this is a two-step reaction, and a two-step reaction is an SN1 mechanism. The 1 here, remember, doesn't refer to the number of steps, but it refers to the number of molecules in the rate law. So let's just clear that up. We see the rate law here. We have only one molecule, only one reactant is in the rate law. Whereas for the SN2 mechanism, right there, the rate law has two reactants. Here the rate law has one reactant. And so now let's turn back to the question and we'll be able to understand it better. So let's just take a look. So here's our question. And so we said the first one, primary halogen alkanes react mainly by SN1 mechanism. No, that's wrong. That's for the tertiary. Chloroalkanes react faster than iodoalkanes. So what is this referring to? This is referring to the carbon Cl bond or the carbon iodine bond. And the one that's going to react faster is the one which has the weaker bond. And how do we know which one has the weaker bond? Well, the iodine has a weaker bond, and we know this because if we check the bond enthalpy and you have the bond enthalpy in your data booklet, otherwise you should know that the carbon iodine has a weaker bond enthalpy, a smaller bond enthalpy than the carbon chlorine. And so since it has a smaller bond enthalpy, it's going to take less energy for it to break. And therefore, this is also wrong because the iodoalkane has a weaker bond, and therefore the bond breaks faster, and therefore the iodoalkane will react faster because the weaker bond breaks faster. Now, if we look at number C, or letter C here, it says tertiary alkanes react faster than primary halogen alkanes. So this goes back to the speed of a SN1 versus an SN2, and we saw that the SN1 mechanism, which is the tertiary alkanes undergo the SN1, is faster. And why is that? It's because of the transition state. If you remember, the SN2 mechanism has a transition state. Just let's take a look at that again. The SN2 mechanism has this transition state right here. And that transition state has a high activation energy. That transition state has a high activation energy. Because it has a high activation energy, it is going to be slower. So the SN1 mechanism, or SN2 mechanism, is slower than the SN1 mechanism because the activation energy of the transition state is higher. And so now, going back to our question, so C, tertiary halogen alkanes react faster than primary halogen alkanes. That is the correct answer. Now, let's take a look at why D is then incorrect. So D says the rate of the SN1 reaction depends on the concentration of the aqueous sodium hydroxide. So in order to find what the rate depends on, we'll want to look at the rate law. The rate law for a SN1 and a SN2. So, for the rate law of the SN2 reaction, you have hydroxide here, and you have the halogen alkane. We'll just say HA. But in the rate law of the SN1 mechanism, you only have the halogen alkane. There is no hydroxide in the rate law for the tertiary halogen alkane, which goes by SN1. So then, therefore, this is also wrong because there's no hydroxide here. There's no hydroxide in the rate law. And therefore, if there's no hydroxide, this rate will not be affected by the concentration of hydroxide. So if you remember, here we see that the rate law, this was the rate law of the SN1 SN1 mechanism. And the SN1 mechanism, notice there's no hydroxide there. So the rate only depends on the halogen alkane. Whereas for the SN2, the rate depends on both the halogen alkane and the hydroxide. So for the SN2 mechanism, hydroxide will affect the speed of the reaction. But for the SN1 mechanism, hydroxide will not affect the SN1 mechanism because there is no hydroxide in the rate law. So that's the question. So C is the correct answer, and I hope you should understand now why A, B, and D are the incorrect answer.